Hi, I'm Eva Murphy from Electronic Engineering at IT Sligo, and this is my Leaving Cert Maths Grinds channel. I'll regularly add new videos for both higher and ordinary level maths, so make sure you subscribe below and click the bell icon to be notified of new videos. The 2015 question on probability on the Leaving Cert course. In basketball, players often have to take free throws. When Michael takes his first free throw in any game, the probability that he is successful is 0.7. For all subsequent free throws in the game, the probability that he is successful is 0.8. If he's been successful on a previous throw, 0.6 if he was unsuccessful. Okay, find the probability that Michael is successful with all three of his first three throws. Okay, so the probability of success, success, success. The reason this question is difficult is because the probabilities change depending on previous events. Okay, so you would definitely say these events are not independent. Okay, in other words, it does matter what happened before it. Okay, so it's his first three free throws. So the reason I underlined it is his first free throw in any game has a different probability. So that first one is 0.7. Okay, he's successful with all three. So he was successful in this one. Okay, so therefore his next one will be 0.8. Okay, his confidence is up, so he is more successful now on his throw. He was successful here, successful here. So again, it'll be another 0.8 for that throw. And let's put that into the calculator, 0.7 by 0.8 by 0.8, and I'm getting 56 over 125, or if we change it to a decimal, whichever way you want, 0.448. Find the probability that Michael is unsuccessful with his first two free throws and successful with his third. Well, if he's unsuccessful with his one, well, you know that the probability of success plus the probability of unsuccessful must equal 1. All probability has to add up to 1. Okay, so on his first one, if that was going to be 0.7, then the probability that he's unsuccessful on the first one has to be 0.3. Okay, in other words, I'm doing 1 minus this 0.7, which was the probability that he was successful on the first one. Okay, so 1 minus 0.7 gives me that 0.3. So that's his first unsuccessful. Okay, we then move on to his second unsuccessful. Okay, so 1 minus 0.8 is 0.2, 1 minus 0.6 is 0.4, 1 minus 0.7 is 0.3. Okay, so he was unsuccessful in this one, therefore it's the pink option here. Okay, it's 0.6 if he was unsuccessful. So therefore the probability that he's unsuccessful again is 0.4. Okay, and then he's going to be successful. So, okay, it's not that one because that's only relevant to his first throw. It's either 0.8 or 0.6. So I have to look at the one before it. It was unsuccessful. So it's going to be a 0.6. Okay, so into the calculator, 0.3 by 0.4 by 0.6. And I am getting 9 over 125 or 0.072. Okay, list all of the ways that Michael could be successful with his third free throw in a game, and hence find the probability that Michael is successful with his third free throw. Okay, well, okay, he's going to take 3 throws. So he could be successful, successful, successful. Okay, so in all of these, he's going to be successful on his third one. I don't know how many I need, okay? He could be successful and unsuccessful. He could be unsuccessful and successful. He could be unsuccessful and unsuccessful. And that's all that there is. Okay, so they are all the different options that Michael could be successful on his third throw. Okay, it didn't state anything about the first two throws. So that is why you have to take all of the different options. Okay, you can't just have an isolated third throw. For there to be a third throw, there had to be a first throw and a second throw. Okay, and of course, the key word between all of these is successful and successful and successful, and so on and so forth. Okay, and then I have or between the lines. Okay, so for him to be successful on his three throw, he can be SSS or SUS or USS or UUS. Okay, and then you fill in your probabilities for each of these scenarios. So successful with the first is 0.7. This is the top one we did, isn't it? So it's 56 over 125. The second one, he's successful on his first. He's then unsuccessful on the second one, and you just have to be careful at all times as to which of these two lines you're on. So he was successful in the first. So the probability that he's unsuccessful is a 0.2. Okay, and then he's successful again on his third one. Well, he's had a miss, so his confidence is down. So it's a 0.6 for that one. Okay, 0.7 by 0.2 by 0.6 equals 21 over 250. Okay, and then the third one, unsuccessful, is going to be 0.3. Okay, it's the opposite of the 0.7 that's there. He's unsuccessful here, so his success is going to be the 0.61. And then he's successful again, but he was successful before it, so the last one is 0.8. 0.3 by 0.6 by 0.8 is 18 over 125. Okay, and then the last one, UUS, is the one we had here in part B, which is 0.3 by 0.4 by 0.6 being equal to 9 over 25. You put a line over all of them and you add them up, 56 over 125 plus 21 over 250 plus 18 over 125 plus 9 over, I presume that should be 125. Okay, let me put in the 1. And I'm getting 187 over 250 S to D him, and I'm getting a probability of 0.748 or 74.8% chance that Michael, is that his name? Yeah, is going to be successful on his third throw. Okay, so that was the first half of that question. It's a long question. You can see there's another 3 bits and another 3 bits here. It's one of the long questions at the end. Always know 7, 8, and 9 are the long questions. Typically, they're the hardest questions because they merge many chapters together. Okay, 2019 paper was a very unusual paper because I thought that particular paper had easier long questions at the end and harder short questions at the front, okay? And that was the first time I'd really seen that. Up until then for Project Maths, which really started in 2012-13, the short questions tended to be easier and the long questions at the back tend to be the hard ones. Okay, but anyway, my point being this is a long question from the back. Right, so I think from here on in now it starts to get a bit hairy. Let Pn be the probability that Michael is successful with his nth free throw in the game, and hence 1 minus Pn, so he's either successful or not successful, is the probability that Michael is unsuccessful with his nth free throw. Okay, so Pn, he's successful. 1 minus Pn, he's unsuccessful. Show that P of n plus 1. So show that for his next throw, the probability is 0.6 plus 0.2 times Pn. Okay, so this is what we call the generic case, where you take eighth row Pn, and now we're looking at, well, what can we come up with a formula that would describe the probability of his next throw. Now, as you know, the probability of his next throw depends on whether his previous one was unsuccessful or successful. Okay, so it's 0.8 if it's successful. It's 1 minus 0.8, or it's 0.6, sorry, if he's unsuccessful. Okay, because we're looking for the probability of n plus 1. Okay, so the probability of success is Pn. The probability of unsuccess is 1 minus Pn. Okay, and of course there's an or in the middle. So the probability of n plus 1 is equal to 0.6 times 1 minus Pn, or is plus 0.8 times Pn. Let's multiply that in. 0.6 by 1 is 0.6. 0.6 by that is minus 0.6 Pn. Here I have plus 0.8 Pn, so it's equal to 0.6 plus 0.2 Pn. Okay, so QED, which is Latin for proven. Okay, that was hard. Now, assume that P is Michael's success rate in the long run. That is, for large values of n, we have P to the n plus 1 being approximately equal to Pn, being approximately equal to P. I hope you can see that, okay? So those two little squiggles means approximately equals to. It's maths language for approximately equal to. What they're saying, basically, use the results from from D part 1 above, show that little p is equal to 0.75. Basically, what they're saying is, if you do enough events, or in other words, if Michael shoots enough hoops, what is the probability that he scores? Okay, so you know the way it's 0.8 if he was successful on the previous one, 0.6 if he was unsuccessful on the previous one. Well, basically what they're saying was, if you take enough shots, it's going to more or less average out to 0.75. Okay, so we have to show that. Okay, and it says use the result from part D. So let's take down that result from part D, which is p to the power of n plus 1 being equal to 0.6 plus 0.2 times Pn. Okay, and then what it's saying is P of n plus 1 is approximately equal to Pn, which is approximately equal to P. So I would say that that's approximately equal to P. Well, 0.6 is 0.6 and 0.2 times P. Okay, so in other words, the probability of all of them is in and around the same. It's this value P because we're taking so many shots. Okay, then we solve for P. So I would say that this P over here minus 0.2p is equal to 0.6, or I have, that's 1p minus 0.2, 0.8p being equal to 0.6. Divide both sides by 0.8, so that I have p being equal to 0.6 divided by 0.8, and I do get 3/4 or 0.75. Okay, I remember that year students did get this part and never got this part. Okay, so a good question, a question well written in your Leaving Cert will not have all of the parts chained together. They will have breakpoints where you can continue the question because they gave you the answer to the previous part. Okay, so look out for that. Don't assume that just because you couldn't do this part automatically meant you can't do these two. Okay, and then the rest of this question then went into sequence and series, For all positive integers n, let an equal to p minus pn, where p is equal to 0.75 as above. Use the ratio a of an plus 1 over a to the n to show that an is a geometric sequence with common ratio a fifth. Okay, so a to the power of n is just a term in a geometric sequence. Geometric means it's multiplied or divided by the same amount rather than it add or subtract the same amount. Geometric is a multiply or divide type sequence. A to the power of n is just a generic term. A to the power of n plus 1 is one term above that. Okay, so the theory of a geometric sequence is that when you divide one term by the one before it, you should get what's called a common ratio, which is a fifth. Okay, so in other words, the relationship from term to term in this sequence is a fifth. So the second one multiplied by a fifth gives me the third one, and so on and so forth. Okay, so this isn't easy. A to the power of n is p minus pn. So a to the power of n is p minus pn. Okay, so that's the bottom. I just subbed in here for an. And then the top line is a to the power of n plus 1. So just like in functions, n here is being replaced by n plus 1. So I would replace this n by n plus 1. So on the top then I would have p minus p n plus 1. Okay, so I hope that makes sense to you now. What's that equal to? Well, p is 0.75. Okay, so 0.75 minus, right, p of n plus 1. Have we a term for p of n plus 1? We do, we have it here. Okay, so here. So that's minus 0.6 plus 0.2 pn. And then pn, in the other hand, is pn. Okay, not too much I can do with that. Okay, let's try and work that out.
You know the way you've written up the top, successful 0.8 is pn. Is that related to that, the question that we're doing now?
Yes, so those two combined gave me this. And that's going in here. So it is loosely related.
Could you sub in 0.8 for the pn that you have in the bottom line?
No, I don't think so, because you can't, because the 0.8, you'd have to know that the shot that came before it was successful.
Oh yeah, okay.
But what I'm wondering is, could I sub in the 0.75? That's what I'm wondering. Okay. But I'm thinking not. Okay. So what I'm going to do is I'm going to work out the brackets here like this and see where does it bring me. Okay, I'm hoping, because I'm showing that it's a fifth, that the PNs are going to somehow cancel. That's what I'm hoping. But let's see, does that happen? Okay, so 0.75 minus 0.6 is 0.15 minus 0.2 PN is on the top. And I still have 0.75 minus PN. Okay. Now, here's the leap of faith, okay? I see that this one is 5 times bigger than this. Okay. I'm laughing because I'm kind of going, it depends on the day as to whether you would see this. So I factorized the bottom one into 5 times 0.15 minus 0.2 pn. 5 times 0.15 will give me 0.75. 5 times minus 0.2 gives me the 1 that's here. Now, the reason I knew how to do that was I'm trying to force my answer to be a fifth. Okay? So it's a bit that I knew what the answer was. And I kind of in my head worked backwards. I knew that somehow I needed a 5 on the bottom, and I knew somehow I needed these PNs to cancel. Because that PN, the probability, is, as was said, dependent on whether it was successful or unsuccessful before. Okay, so that's that piece of the question done. Okay, so the continuation of that question then, part 2, find the smallest value of n for which p minus pn equals or is less than that tiny number that's there. Okay, find the smallest value of n. So a couple of things. Remember, this is a geometric sequence. Okay, we want the smallest value of n. So let me find sequence and series, wherever they are. Here. Okay, so here's your geometric sequence, page 22 of the log tables, and any term in a geometric sequence is equal to a or to the power of n minus 1. Okay, so Tn is equal to a or to the power of n minus 1. So I want to know what n gives me a value which is less than that. Okay, so if I look at the first term in this sequence, which I could call, well, actually they're calling them A's. I normally call terms T, but we can change it to A. So my first term, which we call A1 or T1, if you noted that, is equal to, well, I have to find my common difference first, don't I? Yes. Let me find my common difference first so that I can then do that. Okay, so remember our probability P is equal to 0.75. Okay, so that's the probability for, it's the average probability that we took when we take a lot of shots. Okay, and remember that the probability of my first shot was 0.7. Okay, so therefore, to work out what was my very first A, I would go 0.75 minus 0.7 to give me 0.05. Okay, so this would have been my very first, I suppose, term in this geometric sequence. Okay, and then it builds up. Okay, so then to find this and solve it for n, I would say that this A is 0.05. My or is a fifth, which we found in the last one, to the pi minus 1, because or is the common ratio here. And we have to show that's less than 1, 2, 3, 4 zeros. 1, 2, 3, 4 zeros. Okay, I would divide both sides by 0.5. Okay, and let me just put that into a calculator. 0.0.001 over 0.05. Okay, and then when what you need is in the power, you have to use logs. Okay, so you can use the switch, or you can use, I tend to use this one here. Okay, so let me show you how I use that. Well, the base number there is a fifth, so I know if I go log of a fifth, what I do to one side, I must do to the other. Okay, and if you look at that rule, when the base number here, the base of the log, matches the base of the power, they cancel, and you're just left with what was in the power. Okay, so what I'm hoping here then is the fifth and the log fifth cancel, so that I'm left with just n minus 1 being less than, but what I did to one side, I have to do to the other. So onto my calculator, you don't hit the button called LOG, you hit the one that looks like this, log with a box here, with the box here, because this one allows you to put in your own base number. This log button that's on your calculator is defaulted to log to the base 10 because it's the most common log that we use. So this is the one that you need, not that one. Okay, so log, and I'm putting a fifth into the power or into the base of 2 by 10 to the minus 4. Okay, you just clean off a little bit. And if you can get that into your calculator right, I am getting 5.292. Bring over the 1, n must be less than 6.292. And I presume it's to the smallest value, which is 7. Okay, so quite a difficult question there for part 2. Okay, F. You arrive at a game in which Michael is playing. You know that he's already taken many free throws, but you do not know what pattern of success he has had. Based on this knowledge, what is your estimate of the probability that Michael will be successful with his next free throw? Well, if he has already taken many free throws, then we're going to use what we're assuming the probability to be, which is 0.75, because isn't that the value they said to assume for P? Why would it not be appropriate to consider Michael's subsequent free throws in the game as a sequence of Bernoulli trials? Well, they're absolutely not, because the probability is not the same for each event. In other words, it's 0.8 if he was successful before, it's 0.6 if he was unsuccessful. So the probability is not the same for each event. The events are not independent. Okay, so that includes that not so very nice question. If you've enjoyed this video, then why not join us in IT Sligo and use maths in practice. In conjunction with industry, we've designed an exciting new program in electronics and self-driving technologies, which uses cutting-edge techniques such as artificial intelligence, computer vision, and virtual and augmented reality. You'll need a H5 in maths to qualify. Check out the link below.